Hi everyone. In this video, we're going to start chapter 16, the normal distribution. The normal distribution is basically used a lot in statistics, especially if, and probably only if, the data is symmetrical. So you can see the two curves I have on the screen. We call that a bell-shaped curve. So you might sometimes hear people refer to a bell-shaped curve or something that is normally distributed. That just means that it is symmetrical. So what we basically have, and I might just draw this to the side. Come on. Okay, so we've got our bell-shaped curve. Oh, it was going to be a perfect curve too until I got to the right side. And in the middle here is your mean. All right, so we always have the mean in the middle, okay, represented by mu, and that's the same as your median. Okay, so when you've got data that is symmetrical, your mean and your median are the same, and it's that peak there. Also with the normal distribution, the standard deviations are spaced the same. So you can see in these diagrams, and I'll talk about that in a sec. So, and we've kind of touched on this already. Okay, so remember we were talking about 95% of the data fit within 2 standard deviations of the mean. So here's minus 2 standard deviations, and here we have plus 2 standard deviations. So just using mu, and that area there is 0.95 or 95%. Now, let's have a look. Let's try to focus more on the normal distribution. So in your textbook, I couldn't really find what I liked, the diagrams that I liked, and obviously the one I just drew isn't the best, but I've looked at 16b because 16b does kind of complement 16a. So I'm going to talk about 16b here, but I'll do a separate video for 16b anyway. So if we look at these two curves, so the figures below show how standardizing IQ scores transforms a normal distribution with a mean of 100 and standard deviation of 15 into the standard normal distribution with a mean of 0 and standard deviation of 1. So let's take IQ scores. So people who, psychiatrists or psychologists have developed this scale for your intelligence. Okay, so IQ stands for intelligence quotient, I think. So the majority of the population, the mean of the population have a IQ of 100. Okay, so that's your average IQ, 100. You're either above or below 100, or you could be a 100. And, they say people who are geniuses, are around, I think above 140. Okay, so we kind of say that, well, there's not many people in this little portion here. Okay, it's very rare for someone to be a genius. Okay, so we say the mean is 100. So the average person, has an IQ of 100. If we were to standardize that, we then change it so the mean is 0. Okay, so we've got our general normal distribution and then our standard normal. So we can sometimes we can standardize things just to compare. And when we do a bit more of chapter 16, that will probably make sense. Or if you do further maths, you'll be familiar with this normal distribution. So basically, the top curve is just looking at the raw data. So looking at the mean of 100 and the standard deviation of 15. And then your standard normal distribution just converts everything so that your mean is 0 and your standard deviation is 1. So then you say how many standard deviations you are from the mean. So for people with an IQ of, say, 145, are 3 standard deviations above the mean. Now, the reason why we do that, I'm just going to get the textbook up, and this is in 16b, is we use this rule. So on average, 68% of people, so if we look at this first curve, 68% of people would be 1 standard deviation either side of the mean. So if we were thinking of IQ, let me just get that back up, 68% will be between 85 and 115. Okay, so 68 between 85 and 115. All right, if we were looking at 2 standard deviations, and we've already done this, 95% of people would be between 2 standard deviations below and 2 standard deviations above. And that's 95% of the population. So the majority of the population would be within 2 standard deviations. So if I go back to my curve here, so 95% of the population would be between 70 and 130. Okay, and you would expect that because we're getting wider and wider. All right, and let's just go to the last one. So 99.7%, so nearly 100% of the population is within 3 standard deviations of the mean. And you can kind of see with this curve, and we're going to look at the equation for the function of that curve in a sec. But basically, it keeps going closer and closer until it gets to the x-axis, but the x-axis acts as an asymptote, so it never actually crosses it, but it gets closer and closer to it. So the majority of the population is 4 standard deviations either side of the mean. So it can't be exactly 100% because it doesn't stop at -4 and 4. It goes on to -infinity to infinity, because obviously if you're thinking of IQ scores, sorry to keep switching, you could have someone with an IQ below 40, and you could have someone with an IQ above 160. It's very rare, okay, because if you think about this curve, it's going to be closer and closer, so the area under that curve is going to be extremely small. All right, so that's what the normal distribution is. Okay, so the area, and how it relates to what we're doing now, is the area under that curve is equal to 1 or 100%. Okay, but it does go on from -infinity to infinity. So we don't have end points. All right, so just quickly, the standard normal distribution, as I said before, has a mean of 0. Okay, and there's its peak there. So if I just scroll up, there it is. Okay, the same curve, but it's now just put on a set of axes. And with a standardized normal distribution, you have standard deviation of 1. Okay, so it's the same as this curve here. All right, so they're the same. It's just been put on a set of axes. Now with your standard normal distribution, you do have an equation. So that curve is represented by this function here. Okay, so if you were to graph that, you would get this curve. Okay, so it's a little bit complicated and there's no point in me reading it out. But with a standard normal distribution, you will always have a mean of 0 and a standard deviation of 1, always, when it's standard. Okay, so if it's just a normal distribution, it's not going to be 0 and 1, but when you standardize it, it's going to be 0 and 1. Okay, so just remember that. Okay, so there's your standard normal distribution. So a mean of 0 and a standard deviation of 1. But if we look at the general normal distribution, okay, which is kind of what we had up the top here with this, the IQ scores, okay, the first one, we don't have it standardized. We're going to keep the mean of 100 and a standard deviation of 15. So you can see here the rule looks quite similar to before, but we've got now the standard deviation there, which you did have there, but because for a standard normal distribution, the standard deviation is 1, so 1 times root 2 pi is still root 2 pi. And then we've also got up here x minus the mean over your standard deviation. So if you were to have a mean of 0, so that just becomes x minus 0 over 1, which just gives you x squared anyway. So they're the same function. So this one here and the one above, they're exactly the same, just the one up the top has a mean of 0 and a standard deviation of 1 substituted into this. Okay, so exactly the same thing. All right, and then if you want to know the probability, there's a formula there. So we're going to apply that in a sec. You just need to take note of A. So A goes here, and then your mean, and then your standard deviation. All right. So normal distribution is used a lot in statistics, but it only applies if the data is symmetrical. Okay, so but what I mean by symmetrical is it takes on this bell-shaped curve. All right, it must look like that. All right, so let's go on. We're not going to do any questions just yet. All right, now let me just see if I need, so with the normal density function, we're just really looking at the mean and the standard deviation. Okay, so depending on your mean and your standard deviation, your curve, your normal curve is going to change. It's going to have the same shape, so your mean is always going to be this peak, but if you've got a small standard deviation, it's going to be quite a steep curve. If you've got a large standard deviation, it's going to be flatter. Okay, so we'll have a look at that in a sec. So let me just go through any important points. So again, your probability corresponds to the area under the curve. The total area under the curve is 1. But remember that will go from negative infinity to infinity. Its center is determined by the mean, as I showed you. That peak is your mean. And its width is determined by the standard deviation. So the smaller your standard deviation, the taller your curve is going to be. All right, so let's have a look at a couple of examples. So for this first one here, we've got two curves that look exactly the same. The only thing is they have different means. Okay, so the first one has a lower mean than the second one, but they've got the same shape because the standard deviations are the same. Okay, so the standard deviation of the first one is equal to the same as the second one. So they've got the same shape. Okay, so that's because your standard deviations are the same, but they're at different points on your x-axis because the mean is different. So you might want to say this one has a mean of maybe 5 and this one has a mean of 15. Okay, so a higher mean, but your standard deviations are the same. So maybe you can say the standard deviation of the first one is 2 and the standard deviation of the second one is also 2. So they have the same shape, just different means. All right, in the second example, for this one, they've got the same mean. Okay, so we're looking at this one here. So they've got the same mean. So you can see they've got the peak the same. So the mean of the first one and the mean of the second one are the same, but they do have different standard deviations. So you can see with the blue curve, it has a smaller standard deviation. So maybe we can say the standard deviation of the first one is 2 and the standard deviation of the second one, and I'm just making up numbers here, could be 4. All right, so it's wider, but the area is the same. Okay, that's why you can't have the red peak at the same x value, but its peak is lower for its y coordinate. So it's important to note that the area under the curve is always the same. Okay, so we know for a probability density function, the area should always be 1. But no matter what the mean and standard deviation is, these percentages are always the same. Okay, let's just go back. We've got more theory. All right, so let's have a look at some questions. I might just make this a little bit smaller. All right, so for question 3, consider the normal probability density function. So what we've got here is it's just the rule for a normal distribution, but you can see that this value here is your mean. And no, sorry, that's your standard deviation. Getting my values incorrect. So, oh, why did all right, that's your standard deviation, and there's your mean. Okay, so your mean is 2, so you can read it straight from your function, and your standard deviation is 3. All right, so for part A, use your calculator. All right, so it's probably just showing us or proving that these are true. So let's get that up. Now I'm going to define this because it's quite a tricky one. So I'm going to define f of x. Okay, so while I'm doing this, you can put it into your calculator too. Just make sure everything goes in properly. There's a lot going on here. Oops, I need that. X minus 2 over 3. All right, so I've defined it. Now I know what it's asking me is basically to prove that it's 1. So let's just prove that it's 1. So I'm going from negative infinity to infinity. And just so I don't have to type it again, I can just do f of x. I always don't think it matters if I typed it in, but let's just do this. Okay, so there it is, it's 1. Okay, so it's just proving that the area under that normal distribution is 1. All right, for part B, part I, it's asking us to find the expected value. So the expected value is the same as the mean, and I already know the answer is 2 because I could identify it from the function. But basically it's saying let's prove it using the calculator. Okay, so I'm going to get my definite integral up again. Okay, so actually what I'm going to do, let's just copy and paste this. All right, so we know to do the expected value, it's x times our function. So I'm just going to put x times in there. And I know it has to equal 2. And there it is. Okay, so just, identified it from the function, but I can also prove it on the calculator. Okay, so maybe I'll just write that down for the benefit of those who would like to write it down. So let's let f of x equal, so on CAS, and then we're doing, what was it, f of x dx, and then we should get is 1. And then for B, we're going from negative infinity to infinity, x times f of x dx, and the answer is 2, which we know, we saw that before. All right, and then for part C, it's actually getting us to work out the variance and then find the standard deviation. So I already know the standard deviation is 3, because I could identify it from our function. But let's just go ahead and do that. So I'm going to just highlight and drag it down. So if we're doing ex squared, I'm just going to change that to be x squared. Okay, so we did do this in in chapter 15, sorry. All right, so let's do C over here. So we're going from negative infinity to infinity, x squared, f of x dx is equal to 13. So e x squared is 13. And then to calculate, so the variance we've got to do first. So your variance is equal to ex squared minus minus the mean squared. So 13 minus your mean, which was 2. So that's going to give you 9. So your variance is 9. So that means your standard deviation is the square root of 9. And that could be plus or minus 3. And we know it has to be positive 3. I might need to do that. Okay, so we've just calculated it there, but I didn't really have to do any more on the calculator either, okay, because I was just doing 13 minus 9. All right, so that question there is just getting you to identify your mean and standard deviation in your function and using your calculator to prove it. So if you've got your function there, you don't need to do all that working on your calculator. All right, question 4 is exactly the same. All right, so perhaps have a go at doing it on your own. So I can, oops, I was just about to cross out that 5. So there's your standard deviation, which is also here, 5. And then your mean, see how it says plus 4? You've got to read that as x minus negative 4. So your mean is negative 4 and your standard deviation is 5. So if you want to go ahead and do that on your calculator, it's exactly the same as what we did before. So I'm not going to redo that one just to save time with the video. All right, so for question 6, again, they've given us the function, which is good. All right, so what we've got here is, oops. Okay, so that's where our standard deviation usually is. Now it's not, there's no number there, but there is, it's just the number 1. So your standard deviation is equal to 1. And then with your bracket here, we've actually got x minus negative 3. So your mean is equal to negative 3. All right, so write down the mean and standard deviation of x. So we've just done that. When you're sketching your graph, because it's a normal distribution, we can just go ahead and draw a curve. Now, oh, it doesn't matter if it's peaked or anything like that, because where it peaks, sorry, because it's just your mean and your standard deviation that you're going to fill in. All right, so your mean is always in the middle. Okay, so there. All right, didn't mean to do that in highlighter. So that's going to be negative 3. All right, that's your mean. And then our standard deviation is 1. So we're going to go, now you should do probably 4 each side, at least 3. What's that? 1, 2, 3, 4. And we're just going up and down by 1. So negative 3, negative 2, negative 1, 0, 1. And then we've got negative 4, negative 5, negative 6, negative 7. All right, so that's going to form our x scale or x-axis. And then your y-axis, oh gosh, sorry, that's very bad. Okay, so that's your x, and there's your y. Now, we didn't talk about this peak here, so this turning point might just go back to the textbook. Just bear with me. All right, so you can see on this in the center here that this value here is the y-coordinate of the turning point. So 1 on mu root 2 pi. Let's see if I can remember that. 1 on mu root. No, it's not mu, that's sigma. 1 on sigma root 2 pi. I'm going to forget that. Okay, so we've got 1 on sigma times the square root of 2 pi. Now I can just substitute in sigma. So 1 on root 2 pi. So if you wanted to get the coordinates of that point there, it's just going to be negative 3 and 1 on root 2 pi. Okay, let's move on to question 8 and then we're nearly done. Okay, describe the sequence of transformations which takes the graph of the probability density function of the standard normal distribution to the graph of the probability density function of the normal distribution with. Okay, so remember our standard normal distribution, and I'm going to draw that in a second. Okay, so it has a mean 0, so it kind of sits on the y-axis there, and a standard deviation of 1. Okay, so for the first one, for question A, we've got a mean of 3 and a standard deviation of 2. So what the mean does, it just moves it to the left or the right. So for question A, so first of all, we've got a mean of 3. So it's translated 3 units in the positive direction. Terrible handwriting today. Of x-axis. All right, so I don't have to sketch that, but if I did, okay, your turning point would now be up here. But because you've got a standard deviation of 2, your graph now becomes flatter. So it's actually, if I scroll, oh, no. Actually, yes. Sorry, let me just scroll up. So you can see what has happened with this first graph. All right, so this, I know you can't see my cursor. So this one here, the mean, see how it's had a translation, a horizontal translation. And this one here, we've got a dilation. Okay, so the mean, just if your mean changes, then you've had a horizontal translation. If your standard deviation changes, then you've had a dilation. All right, so let's just go back down to the question. All right, and then your standard deviation, oops, change color. We've had a dilation factor of 2 from the y-axis. So you've had a dilation from the y-axis. If you want to, you can say the same thing, but from the x-axis. So I'm just going to write or dilation factor of 1/2 from x-axis. Okay, so you can say dilation of either one, so either from the x-axis or from the y-axis. Okay, so the mean tells you your translation, and your standard deviation tells you your dilation. Okay, so for B, we've got the same translation, so I'm not going to do that one again, but this time we've got a different standard deviation. So this time it's 1/2. So you can say it's a dilation factor, probably not using the right words here, of 1/2 from y-axis, or if you want to say it's from the x-axis, then it's 2 from x-axis. All right, and then for part C, this time we've got a different mean, so it's -3, so that means it's gone to the left. Okay, so let's write that one down. So we've got a mean of -3, so translated 3 units in the negative direction. Along the x-axis. Okay, so make sure you write 3 units, not -3 units. That negative just tells us we're going in the negative direction. And the standard deviation of 2 you can write is the same as question A, so you can write the same for question A. So dilation factor of 2 from the y-axis, or if you want to do it from the x-axis, it's a dilation factor of 1/2. All right, girls. Bye.